Okay, question number 7. Smera, what's your answer?
Sir, I got A.
Okay. Vaibhav,
Yes, sir.
what's your answer, Vaibhav, for 6th, 7th?
Oh, 6th and 7th, I got A.
Okay, and Samir?
So for seventh question, right?
Yes,
Yeah, 7A.
good. Sheldon, did you get A as the answer?
For question 7, I got my answer as A.
Ah, correct. So all of you are right. So this is like a basic. We had we had I taught you this in the class. Okay, never mind. So 8th question. Now this is interesting. Smera, please tell me what's your answer.
Sir, I got A.
Nice. Okay, Vaibhav,
Same thing, so I got A as well.
Sheldon, did you get A?
So I did get A for this. However, I did not get it properly because I guessed the actual answer.
Okay, so I'll
I can't
explain.
really say
What
that I
about you, Samir? What's your answer?
Yes, sir, A.
Could you explain the logic? Yes, the answer is A for this. What is the logic?
So since this is the Celsius scale and not the Kelvin scale, we can safely conclude that it won't start at the origin.
Correct.
And since 0 Kelvin is minus 273 degrees, the line has to start at minus 273. So it will clearly be A instead of C.
Perfect. Okay, so Sheldon, just pay attention. What we this is the ideal gas equation, right? PV is equal to nRT. Now here T is the temperature in kelvins. So if we draw a graph between pressure and temperature in Kelvin, then the answer would be B, right? But in this question, the temperature is in Celsius, so we need to incorporate that. So how do we do that? Let's say if the temperature in degrees Celsius is given to you, if I add 273 to it, Sheldon, what will I get?
So 1 second. You get it at 273.
So if T degrees Celsius is the temperature in degrees Celsius, if I add 273 to it, what will I get? This
You
is the
get
conversion.
oh, wait up. I'm getting a little confused.
Okay, so Sheldon, we are actually getting the temperature, but in the Kelvin scale. This is the transformation formula. You need to remember this, right? Okay, so basically now take this TK or temperature in Kelvin and put into this. So the same ideal gas equation can be written like nR. In place of capital T, I will write T, which is in degrees Celsius, plus 273. So this is in degrees Celsius. Now if I expand this, I'll get nRT plus nR into 273. Right? So this is PV, correct? Now the question is, we are heating the gas at constant volume. This is given to you, so we can very well eliminate this. So what we will what you will observe is that the value of P, that can be written as nR divided by V into T plus nR 273 divided by V. Now Sheldon, all of these calculations are not necessary, but I'm just explaining you how do we arrive at A. So
Yes,
if
sir.
you arrive here, now you can compare this to our standard equation, which is y is equal to mx plus c. Now the slope will be positive because nr by v is positive and c is the constant term. Now you will see that c is greater than 0, which means this particular line will have a positive slope and positive intercept. So if I check only in part A, the the intercept, the y-intercept is positive. In case of C, if I just if I extend this backwards, you will see that the y-intercept is actually negative. So C is not the right answer. And D is definitely not the right answer because the graph is actually a straight line, not a parabola. So A will be the answer. Is that clear, Sheldon?
Yes, sir. Now I got it.
Okay, great. Okay, coming to question number 9. Smera, tell me your answer.
Sir, I got C.
Okay. Vaibhav?
So I got A.
Okay, Somil.
I actually forgot to do this question.
Okay. What about you, Sheldon?
So for question number 9, I got it as C.
C. So Smera and you got the same answer. Alright, so Smera, could you explain how did you get 4? This is actually
Yeah,
incorrect,
actually, I
but
was
I
like
still
very
want to.
confused about this. So like I sort of like guessed it.
Okay, so the answer which Vaibhav gave is the correct answer. The answer to this is A, 1 and not 4. So this is very easy. This is actually a theoretical question. There is no need to do anything. If your concepts are clear, so I had told you in the class that the kinetic energy of the atoms or molecules only depends on one parameter. Could you tell me what that parameter is?
Temperature.
Yes, so the kinetic energy only depends on the temperature. In this question, temperature is given to you as constant. So whatever masses have been given, those are completely irrelevant in this question. Constant
So, but
temperature.
isn't it 3 by 2 nRT? So even the moles have to be considered, right?
So kinetic energy is 3 by 2 nr delta T. Okay. After this,
So you said that we
so
have to
okay, so
look at
in
the
this, all right,
T
so cool.
only, but the
But
moles
delta
also
T
we
is
don't.
zero. But delta T is zero. So do the same.
Yeah, neither Somil, the doubt is valid, now the number of moles, but in this particular question, is the molecular weight given to you of
No.
x and y, right? If in the exam scenario such a question comes, we have to eliminate that number of moles factor because the data is uh, not clearly given. So n goes out, the r is obviously a constant. So it depends. So the kinetic energy only depends on the temperature. Somil, is it clear? Hello.
Yes, sir.
Okay. So the answer to this is A, 1. Okay. Somil, this tell me the answer to question 10.
10B, B for Bombay.
Correct. Yes. Others, did you get B? Weber?
Yes, sir, I got B.
Yes, I got B.
Good. Sheldon?
So I had guessed it to be B. So I can't really say I've gotten
Okay.
it
So
as
there is
B.
no need to guess here. This is the right answer. See, let's see what is the question asking. During which operations the gas does external work? Now this means gas is doing work, and we have already know the sign convention. When the gas does work, the work is positive. So all you need to check is in which of the processes the sign of the work is positive. And we know the formula for work is P delta V. So whenever the volume increases, work done is positive. Whenever volume decreases, work done is negative. And whenever volume is a constant, then work done is equal to 0. So Sheldon, now can you see RS is the only process where the volume is increasing, and hence the work done will be positive, which is nothing but work is doing external work. Okay, so this is RS, which is option B is the right answer. So Sheldon, you have to use logic and concepts to arrive at your answer and do not guess,
Okay, so
because sometimes see the examiners will put some traps into it. So if your concepts are clear, you can very well answer any question. Okay, 11th is easy. Smera, what's your answer?
Sir, A.
Okay, Vaibhav and Sheldon.
So I got my for question 11, right?
Question number 11.
Yeah. D.
You got D. Okay,
Oh,
Somil.
sorry. C.
Okay,
C.
Somil, what's your answer?
Yes, sir. C.
Sheldon, did you solve this?
so I took mine as C, but I got very, very wrong logic. I think very wrong logic
Okay,
for
could you
this.
explain me the logic?
So can you just scroll up, thoda sa? So as we see over here, the first instinct that came into my mind was, okay, the energy that's going from y and z totally equates to x. However, so can you scroll down for 2 seconds? So the answer is correct. So I was actually very close to taking my answer as A, but I hesitated and I said maybe that could be wrong. So I took it as C because we can visually say that the energy by y is completely bigger and obviously bigger
Okay,
than x.
fair enough. Smera, could you explain to me your logic for option A?
So like I was not sure about this. I just took it like yeah. So for temperature X, like Y and Z are coming. So that's why A.
No, Smera, no. That's not the way how we solve.
Yeah.
See,
But I was
okay.
confused. So
So
yeah.
what Sheldon just explained, that is almost partially true. So see, this is just common sense question. There is no actual calculation involved here, just observation. So the answer to this, correct answer to this is C only, not A. See, all you have to just check is the direction of the heat transfer. So from y to x is the heat transfer going on, which means the theta y has to be greater than theta x, because this is how the heat transfer happens from high temperature to low temperature, right? So okay, okay. So this is one of the relations which you can deduce, and from z to x this is the direction of heat transfer, so we can deduce that theta z is greater than theta x. Now Smira, after this there is nothing we can deduce from the figure which is given. So option A gives a clear cut relation, a linear relation. This is not deducible from the information what is given to you. uh,
Yes,
so,
sir.
so the answer is C and not A. We need to have additional data if we want to arrive at A, but which is not given, so C clearly is the answer.
Okay,
Saumil
sir.
and Vaibhav, what was your logic? The same?
Yes, sir.
Okay.
Yeah, sir.
12th question. Vaibhav, please explain what's your answer to 12.
Um, so I'm pretty sure the 12th one is A. I might be wrong.
Oh,
Um,
that's right. 12th
okay.
is A, A is correct. Saumil, did you get A?
Yeah, sir. A.
Good. Smira and Sheldon, what are your answers?
A.
Okay, Sheldon?
So for question number 12, I did not do
Okay,
it.
see, A
I
is the
think, yeah,
correct
I
answer to
think I've
this.
done it, but I've cut it off. Continue, sir.
So Sheldon, did you mark any option?
No, sir, I did not.
Okay, so Vaibhav, just explain to me how did you get A?
So in an adiabatic process, delta Q is or internal energy is zero.
In internal
The change
energy,
in it.
the delta Q is zero in
Yeah,
adiabatic.
yeah,
Yes,
the change in internal
correct.
energy is zero.
After
And
that,
because it's a compression of an ideal gas, then the
hmm
work done is on the gas, so it's negative.
perfect.
And delta U, well, if it's negative, then I assume that it has to be positive
Yes,
to
it
equal
has
to
to
zero.
be positive. So option number A. So Sheldon, this is easy. Q is equal to delta U plus work done. For adiabatic process, the Q is always zero. Now work done depends either your volume is increasing or decreasing. So since the gas is compressing, so volume is decreasing, hence the work done is negative. Now since the sum of delta U and W is 0 and we know that work is negative, then delta U has to be positive, which gives you option A as the answer. Is it clear, Sheldon?
Okay, sir. Yeah.
Okay, question 13th. Smira, what's your answer?
So C.
Theta plus 273. Okay, and Vaibhav?
So I got D.
Uh, B or D?
D, D, D.
Okay, D for Delhi.
Yeah.
Okay, and Somil, what's your answer?
Yeah, sir. Same. D for Delhi.
All right, Sheldon.
For question number 13, I got it as C.
Okay, so let's go one by one. Smira, please explain your logic.
So because like the metal is heated by theta degrees,
Mm-hmm.
so like in kelvins that would be theta plus 273.
Okay. Okay. Wait. Okay. So Somil,
Because it
could
is
you
asking the
explain?
rise in temperature.
Okay. So Somil,
Yes,
just
I just
explain.
realized my
Yeah, same,
mistake. They
same,
had asked rise in temperature,
same.
not
So,
the final temperature.
Yes. So
yeah,
If
what's
final
the?
temperature was asked, then D would have been the correct answer.
Yes, correct.
yeah.
Understood.
I'm sorry, sir. It's C. Even I got that one.
Even C is incorrect. Could you please figure out? Even C is incorrect. C and D both are incorrect. Just read the question carefully.
Sir, see, I did not understand what the B option was. It was just a dot.
B is
So,
just theta.
So it is B.
Oh,
So it has to be B because the change in temperature in Kelvin and Celsius are the same.
Absolutely
oh,
correct. So the answer to this is B and not C or D. Okay, Sheldon, let me explain what is going on. So a lump of metal was initially at temperature 100. Let's take two general temperatures, let's say TA and TB. Now these temperatures, let's say, are in degrees Celsius, correct? So if I want to find the delta T, that will be just TB minus TA, right? Now consider we convert both of these to Kelvin scale, which means we add the 273 to both. In that case also, if I find the delta T, that will be TB plus 273 minus TA plus 273. This will give you TB minus TA, which is the same as the original delta T, right? So the initially the temperature rise was 3 Ta, which was measured on the Celsius scale. So even in the Kelvin scale, this rise would be the same, 3 Ta. Smera, did you understand the logic?
Yes, sir.
Okay, great. Sheldon, is it clear?
yes, sir, got it.
So you have to remember this as a principle. The change in the temperature, either in degrees Celsius or in the Kelvin, they are the same. The change in the temperature. Okay, good.
Okay, yeah.
Question number 14th. Somil, what's your answer to this?
14th, I got it as D for Delhi.
Okay. Vaibhav?
same, sir. D.
Okay, Smera.
Yes, sir. D.
Sheldon,
Delhi.
did you get D?
No, sir, I did not get B.
How?
I got it as C
Okay, so
again.
the answer to this is D and not C. This is one of those traps I was talking about which examiners do. So the formula for Q is MC into delta T, right? So if I check here, if I write like this, so Q by delta T is equal to MC. So Sheldon, your answer would have been correct had Q been on the y-axis and delta T been on the x-axis. But in the figure which is on your screens, the temperature is on the x-axis and Q is on the y-axis. So the slope for this particular graph is actually T by Q and not Q by T. So this will be 1 by MC. Did you get this, Sheldon?
Yes, now I've gotten it.
Right. So D is the answer to this. Now the last objective question, 15th. Okay, Smera, did you solve this? What's your answer?
So I got D. Delhi.
Okay, but what was the answer?
Like the final answer.
Mm-hmm.
I got 140 degrees Celsius.
140. Okay, let's check. Vaibhav, what's your answer?
Sir, I got A.
Okay. Saumil?
Yes, so even I got A.
Okay, Sheldon, did you solve this question?
So I got it as 120 by doing 80 minus 50 upon 75 minus 50.
So the answer is correct. See, this is the answer to this question is 120. Now, Smera, you would need to cross check. Let me explain the
Yes, sir.
solution. So we had done this particular formula in the class. So if you remember, that formula goes like this. So
Yes.
T minus TL. Okay, let me just name. Let's say TL is the low temperature, which is 0 degrees Celsius. TH would be the high temperature, which is 100 degrees Celsius, right? And so the formula goes like this. So T minus TL divided by TH minus TL, that will be equal to the lengths are given. So L minus LL divided by LH minus LL. Let me explain what each of these terms mean. So T will be the temperature at which the reading is 80 centimeters. So let me just write it here. Temperature and the reading. So when the temperature was 0 degrees Celsius, the reading was 50 centimeters. At 100 degrees Celsius, it was 75. And we need to check at what temperature is the reading 80. So the temperature is what we need to find. So T is that temperature which we need to find. TL is 0. The high temperature is 100 minus 0. Now the L is the length at that temperature which we need. That is given to you as 80. Now LL would stand for the reading at the low temperature, which is 50. And LH would mean the reading at the high temperature. At 100 degrees Celsius, the reading was 75. Now, Smira, if we solve for this, we should get T is equal to 120. Could you check where did you go wrong?
Yes, sir.
And Sheldon, how did you solve this?
So that's exactly how I did it. Firstly, to visualize the entire concept, I took like a small section of my page and I just made a small line 0 to like, I don't know, like 200 or something,
Okay,
and like 100, okay, 0 to 100, and I just visualized it like that, and I correspondingly just made it into 80 minus 50 upon 75
good,
minus
good.
50.
Sheldon, that's a
I
wonderful
did it,
method. Yes, that's
but I
good.
did not. Yeah, but I did not do it like T minus
No,
T2 and all
actually,
that. I
Sheldon,
just
what you have done is the same thing, but that is visually. That's the same thing, both of them.
okay, cool.
So because you won't get the answer till you do these calculations, right? So just check the calculations which you have done might be the just the same.
Okay, cool, sir.
Okay, Vaibhav and
Yeah.
Somin, was your approaches was the same or anything else?
Also,
I didn't directly use the formula, but yeah, I calculated the uh, like degree Celsius per centimeter. I
Perfect.
calculated
Yes.
that value
Yes. So good.
and
So
then I multiplied 5 with it
perfect. So
and
Sheldon
added
did
it
the
to 100.
same thing. So that is like a visual graphical method. That's great. Or either you. So that, this is actually the theoretical representation of what you have done. So Soumil and Sheldon. Okay. Now Smira, did you check?
Yes, sir.
Where did you go wrong?
So I don't know, like I guess some calculation mistake.
Okay. So the answer to this is 120. Just cross check. Okay. Now let's move on to the subjective questions. Question number 16. Smira, did you solve this?
Yes, sir.
Can you tell me your answers?
So, sir, for A, I got 5.066 into 10 raised to 5.
Okay, just a second, let me write it down. 5.066 into 10 to the power 5. Now, Vaibhav, Sheldon, and Somil, did you get this answer?
Yeah,
Sir, I
so
did.
5.07 into 10 to the power 5.
Okay. Vaibhav?
yes, sir. 5.066 times 10.
Correct. Sheldon, did you get this?
No, sir, I did not.
Did you attempt this particular question?
So I tried to attempt it, but I got really confused with the entire question. 'Cause I was stuck at 16 and 17. I was just doing working and working and working.
Okay,
But I
just
get
let me very quickly explain. So, a pressure volume diagram is given to you, and the number of moles is 0.221. And ideal, this is an ideal monoatomic gas. Now, monoatomic means single atom. So, it's like a helium. Helium is a monoatomic gas. So now the graph is given, and at A the temperature is 295, pressure is given. So A to B is given to you as adiabatic. Okay, and the pressure, oh, just a second, this was not supposed to be there. So it's given that for a monoatomic gas, the relation is given to you, which is pressure volume into 5 by 3. This is equal to a constant. And okay, Smera, could you explain? Did you use the same relation to arrive at the answer?
Yes, sir. PV 5 by 3 is equal to, yeah, PV 5 by 3 for both.
Okay, so what we will do is we consider A to B. So initially, let's say PAVA to the power 5 by 3, that will be equal to PB into VB into 5 by 3. Now pressure at A, it is given to you as 1.1 into 10 to the power 5. Now volume at A is also given to you as 5 into 10 to the power minus 3 into 5 by 3. That will be equal to pressure at B, which is what you need to find, and the volume at B is 2 times 10 to the power minus 3 into 5 by 3. Now if we solve for this, Sheldon, the value of PB you should get as this 5.066 or 5.07 into 10 to the power 5. Is that okay, Sheldon? Okay.
Yes, sir.
And Smera, what is the unit for this?
So for A part, right?
Yes,
Pascals, right?
correct. So pascals. Okay. Smera, could you tell me, if I convert the Pascal into SI units, what is the unit of pressure?
Not sure, sir.
Okay, Somil, could you tell me?
I think it's Newton per meter square.
Yes, it is correct. See, because pressure is equal to force per unit area. So force is in Newton, area is in meter square. So 1 Pascal is actually 1 Newtons per meter square. This all of you should remember. Okay, now part B. Vaibhav, tell me your answers.
Part B, so I got 1.52 times 10 to the power 3 joules.
Okay, that is the work. Change in the internal energy.
Um, the change in the entire internal energy would be uh, 2.28 times 10 to the power minus 3.
There is an issue here, but how did you check the change in the internal energy? What is the approach?
The change in internal energy is just 3 by 2 into P into delta V, right?
Just a second, let me write it down. So delta U is equal to 3 by 2 NR delta T. So after this, what did you do?
So since it's mono atom, I just took the pressure and the change in volume. So I just took 3 by 2 into 5.6. Okay, so sorry, sir. That's the change in internal energy.
Yes, that is what
Yeah,
I.
yeah. Sorry. The thermal energy is 3.8 times 10 to the power 3.
No, I am actually after part. This change in the internal energy, delta U value. What did you get? Delta U as?
Delta U I got as 2.28 times 10 to the power 3.
Okay. And the work done? Oh, sorry, the thermal energy transferred.
Yeah, thermal energy I got is 3.8, sir.
Uh,
3.8 times 10 to the
multiplied
power
by?
3. Into 10 to the power 3.
Yes, correct. In delta U, are you getting 10 to the power minus 3 or plus 3?
So I got minus 3 at first.
Okay. Okay, so Samil, could you tell me your answers for part B for this question?
Okay, so work done, I got it as 1520 joules,
1520 joules, correct. That is right.
and delta U, I got it as 2281.5 joules,
Okay. And the work done?
and Q and work done thermal energy, right?
Oh, sorry, thermal energy, yes.
Yeah, thermal energy is just the addition of the earlier two values, so that is like 3801 joules.
Correct. Smera, are you getting the same answers?
Yes, sir. But what I did was like in the question it has was given right. Like pressure at B is about like 5 into 10 raised to 5. So like I used that value
Okay.
instead of the 5.066.
All right. So that is fine. That is okay. So are you getting close answers to what
Yes,
Somil just?
1,500 workers and change in internal energy 2250 and thermal energy transfer is 750.
Okay. Sheldon, I guess I would need to explain, right, the whole process for this, right?
Yes.
Uh, Hello, Sheldon.
Yes, sir.
Okay, so just focus on process BC first. So we have to find the work done, the delta U, and the thermal energy. We know the thermodynamics, the first law, which is Q is equal to delta U plus work done, right? Now for this particular question, we have to use this formula, 3 by 2 nr delta T. There is no need to remember this. This will be given to you in the question, if at all it is to be used. So if I focus first on the work done, see Sheldon, the work done formula is basic. We use pressure into delta V, and we need to find the work done for the process BC. Now Sheldon, just check the graph and tell me what is the pressure for BC.
So the pressure at BC would be 5 minus 2.
No, no, so that is the delta V. That is the change
Yeah.
in the volume. That is 5 minus 2. Okay, let me just write that down. So 5 minus 2 will be 3 into 10 to the power minus 3. Now that is because your volume is in 10 to the power minus 3.
Yes,
Multiplied by
sir.
pressure. Pressure you find by the part A of this question. So either we can approximate that to 5 into 10 to the power 5 or 5.07, which we found in part A. If I multiply these two, the work done, you will get around this 1.52 into 10 to the power 3 joules. Okay, Sheldon.
Yes, sir.
Now this was the work done. This was easy. Now let's see how do we find delta U? Now Weber, you use this formula, right? 3 by 2 nr delta T.
Yes, sir.
Okay, after this, could you tell me the values of what did you put?
Oh, so I use 3 by 2 times pressure times delta V.
Great, wonderful. So see, this is one of the concepts which we have not done in the class, but you have to remember this. So if PV is equal to nRT is your ideal gas, what we can do is we will put delta on both the sides. So we can write this as this delta PV. Okay, let me write it here. So delta PV, that is equal to delta nRT. Now whatever the constant is within the equation, that will come out of the delta. So for the process BC, we can check that is an isobaric process, which means same pressure. So in BC, the pressure remains constant. So this pressure can come out. So we can write P delta V. And on the right hand side, the number of moles and R, both of them are constant. That can also come out. So we can write this P delta V is equal to nR delta T. Now this is an important concept. Please write this as a theory. This will be used in other questions as well. So wherever in the thermodynamics you have nR delta T, you can replace that with P delta V, but the condition is the pressure needs to be constant, because if P is constant, only then the P comes out of the delta. Now for example, let's say P is not a constant. In that case, nR delta T will be this delta times PV. So there is a difference between the two. P delta V is when pressure is constant. So please write this down as a theory. And what we have done is nR delta T will be replaced by P into delta V. Now the pressure is what you just figured out in part A, which was 5.07 into 10 to the power 5, multiplied by delta V is the same which we found out here, 3 into 10 to the power minus 3. So if we solve for this, okay, so Weber, did you do it like this, right?
Yes, sir. Same thing.
What was your eventual answer?
2.28 times 10 to the power minus 3.
Okay. Somil, could you check, is it minus 3 or plus 3?
So it's 10 to the power 3. It's 2280.
Weber, please
Oh,
check.
am
There
I?
should be plus 3.
1 second. Yeah, sir. It is plus 3. It is plus 3.
Right. So eventually
I,
this,
value.
Sheldon, see this is the value of delta U, which is 2.28 into 10 to the power 3. So now you have the value of delta U as well as the work. Then the Q is very easily find it out. So Q will be delta U plus work done. So if you add the value of delta U and the work done, the eventual answer of Q will be 3.8 into 10 to the power 3 joules. Sheldon, is this clear? What have we done?
Yes, sir. Yes, sir.
I would want you to write all of this and please revise it after the class. This is important.
Yes, sir. I'll
And
just take a screenshot.
please take a screenshot. And for the others, please remember this. Whenever we have nr delta t, we cannot directly put it as P delta V. That is only when the condition satisfies. Pressure needs to be constant. Only then nr delta t would be P delta V. Okay. All right. Now let's move on to the next part. The process from B to C is B to C originally was an isobaric process. It gets changed into an isothermal. Okay. So Smera, could you explain C?
Yes, sir. So like for C and D, like I was for explanation, it was a little, so I wrote it very short. Like without heat, gas would have like a lower kinetic energy. So therefore, the
Okay.
pressure after the change would be lower.
Okay. Let's see if what you have done is right or wrong. But can you tell me D answer?
So it would increase, right? Because it is a clockwise motion.
What was the question again? Without we have to find the net work done by the engine during one full cycle. Okay. So you are saying it is increasing. Okay. Let's check. Somil, what's your answer to C and D?
So I actually did not attempt C and D. Like I was going to do it at the end after doing all the other questions, but then I
Okay.
ran out
Okay.
of
No
time.
problem. No problem. Vaibhav, did you attempt this C and D?
Yeah, yeah, I did.
So what's your answer?
So
No,
for
first tell me the
part,
D.
sorry,
First tell me the answer to D.
to D. Okay.
Yes, last
Uh,
part.
for D, I got the network would decrease
Okay.
because the area enclosed in the graph is smaller.
Yes, correct. See, that is the correct logic. Okay. Sheldon, did you attempt? Acha, and you didn't, right? Sheldon, you did not attempt C and D, right?
No, sir, I did not.
So,
Yes.
so for D part, like if the pressure is lower, then wouldn't the area of the enclosed portion be higher?
Okay, let us check. Let's go step by step. Let me read the statement again. The process from B to C is replaced by an isothermal process in which the initial state is the same and the final volume is 5. So which means the initial and final volume, they remain the same, but the process converts to an isothermal. And we know the graph for isothermal is like this. So B to C, let's say C dash is the new C for you. This is the isothermal. So now Somil, can you tell me, is the area increasing or decreasing?
So they have said why the pressure after this change would be lower. So
Okay,
if it is
let's
lower, then wouldn't C have to be below A?
okay, let's check. So see, B to C is the isothermal, and in isothermal we know that pressure is inversely proportional to volume, isn't it, Somil?
Yeah.
So now can you check, is the pressure?
Sir, I think he's getting confused. Some you're taking B and A, you're not taking B and C for part C. Part C is asking why the pressure would be lower between B and C, not B and A.
Is that the error, Somil?
Because I don't know, that's one.
Oh yeah, you are right. I was taking it, I was considering it, I was considering BA instead of BC.
Oh, no, 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 no. It is BC. See, the BC graph has been changed to an isothermal one. Okay, anyways, let me explain. So BC dash is your new isothermal process where the pressure is inversely proportional to the volume. So if I focus on B to the new C dash, the volume is increasing, right? Since the volume is increasing and because pressure is in inverse relation, so the pressure will definitely decrease. So that is why how we explain this, explaining without any calculation, the pressure would be lower, right? So, okay, Sheldon, is this clear?
Yes, okay.
Saumil, is it clear now?
Yeah, so the D part is clear, but could you explain the C part?
See, I just did. Says if I just focus on. Okay, let's do it again. Second. All right. So this was your graph. What's the numbers? So B, C, and A. This was your original graph, right? So now they have said is the BC graph was originally an isobaric process. Now this gets transformed into an isothermal, and the isothermal graph is drawn like this. So let's say BC dash. So this is our isothermal where the temperature remains constant. And using the ideal gas law, we know that whenever the temperature is constant, pressure is inversely proportional to volume. So if I focus on B2C dash, what you will observe is that the volume is increasing, and because of this inverse relation, we can say that pressure is decreasing. So the pressure at C dash will be less than pressure at B. Is this clear now?
Understood, sir. Yes, sir, clear.
Now continuing with this, so since the work done is the area of the shaded region, the new area is this. And since the new area is lesser than the original area, we say that the work done would decrease. Okay, so the question was determine without any calculation whether the net work is increasing or decreasing. So we can write this is actually decreasing because the area enclosed by the graph is decreasing. Is this clear to everyone?
Yes, sir.
Okay. Sheldon, it's clear, right?
Yes.
That was question number 16. And we are left with 3, 17th, 18th, and 19th. So this will definitely take time. So should we continue this in the next class?
Yeah, sir.
Yes, sir.
Okay.
Yes, sir.
So please revise whatever we have done and try to attempt. So before the next class, please try to attempt 17, 18, and 19, and then we'll discuss in the next class. So in the next class,
Okay, sir.
the first half we'll do this only 17, 18, 19, and then we'll start off with a new chapter. Okay.
Yes, sir.
Okay, sir.
Now just a second. We are actually going to change the flow of the chapters. Saumil, you had told me, right, the next chapter, what we are going to do is on communications, right?
No, sir, energy production.
Okay, just a second, let me open the book. Just a second.
Sir, I have a small meeting to attend now. Can I join that?
It's okay. Okay, I'll text you anyways the update, so you can join
Yes,
that.
sir. Already. Bye, sir. Thank you.
Okay, so the first, second, and third chapters we have done. The next chapter was circular motion and gravitation, part 7. Okay, Saumil, what was the chapter name again?
Yes, it was 8, energy
8, energy
production.
production.
Like, that's what my school is going to do after that. I don't know about the others.
Okay, Smera, what chapter is coming next in your school?
So, like, we just finished exam, so, like, we will continue with thermal energy,
Okay,
thermal physics.
so you are on thermal, right? Okay, so Weber, what is being done in your school?
Yeah, we're also going into thermophysics. So we're completing mechanics. We're still in mechanics.
Oh, so okay, so you're on mechanics in the school.
Yeah, we're still on mechanics. And
So then
then,
it's fine. So since circular motion is not coming into the picture for you for at least 1-2 weeks, what we will do is we'll do this chapter, chapter 8, energy production. Is that fine?
Yes, sir.
Anyways, this chapter is will not take a lot of time. So from in the next class, the second half, we will start off with this energy production. Okay?
Okay, sir.
Chalo. Great. Take care. Bye bye.
Bye, sir.
that's
Bye,
okay.
sir.